Welcome back to the lecture on radioactivity. This is part 6. Today we'll be looking at simple calculations in radioactivity. In part 5, we took a quick look at the summary of all the formulas used when calculations are to be done in radioactivity. Today we're just going to do a little recap of all the formulas. So let's go through all the formulas again. A quick exam summary. That is, if you're going to sit for SSCE, WAEC, NECO, JAMB, you will need to commit these formulas to your memory. So let's look at them one after the other. Of course, quantity to find, and then the formula you need to use. If you're told to find the remaining atom, that is, number of atoms after decay or disintegration, you will use the formula N equal to N naught base of natural logarithm raised to power minus lambda over t. We defined these terms in our previous lecture. Decay constant, that is lambda, is 1 over t, natural log n naught over n, or your decay constant is 0.693 over half-life, or your decay constant is number of atoms decaying, disintegrating per second over total number of atoms present in sample. Time, you're told to look for time. T is 1 over lambda, natural log, that's ln, n naught over n. Original number of atoms present, that is, n naught is equal to n times 2 raised to power t over t half. Original mass of atom present is m naught is equal to m times 2 raised to power t over t half. Having gone through all the formulas, you will need to commit them to memory so that you will know which to tap from each time you are faced with a problem. So let's see our first example. A radioactive isotope has a decay constant of 10 raised to power minus 5 per second. Calculate the half-life. So then T half is 0.693 over lambda. You need to commit this formula to memory. So T half is 0.693 over 10 raised to power minus 5. Don't forget, we're given the decay constant of 10 raised to power minus 5 per second. So that's it. So if you resolve this, you're going to get that, and finally you get to this point. So let's see question 2. A piece of radioactive material contains 1000 atoms. If its half-life is 20 seconds, calculate the time taken for 125 atoms to remain. So then we employ this formula n naught equal to n times 2 raised to power t over t half. Now, the original number of atoms present, that's 1000. What is left? 125. 2 raised to the power t. We're given that the half-life is 20 seconds. So t over 20 seconds, which is the half-life. So we have to look for t. Divide both sides by 125. That will give you 8 equals to t raised to the power t over 20. That's small t now. 8 is 2 raised to the power 3 equal to 2 raised to the power t over 20. Since the bases are equal, we can equate the powers. This 3 now is t over 20. If you cross multiply, t is 60 seconds. We can also use this formula. That is, t, since we're told to look for time, is 1 over lambda ln n naught over n. Here, we know n naught, which is 1000. Because we're told a piece of radioactive material contains 1000 atoms. So the original number of atoms, 1000. What is left to remain? That is, it says calculate the time taken for 125 atoms to remain. So our n is 125. We don't know the decay constant, but we can use this formula to get our decay constant. That is lambda is 0.693 over t half. The t half is 20 seconds from the question. Once you get your decay constant, we can then use this formula to find the time. So I would like you to attempt that by using this formula and see if you get the same answer. This will take us to number 3. Number 3 says if the decay constant of a radioactive substance is 0.231 per second, what is the half-life? Our half-life again is 0.693 over lambda. We are given the decay constant to be 0.231 per second. So if you resolve this, you're going to get 3 seconds.